Welcome to the Deep Dive, your shortcut to getting informed. We sift through the sources, pull out the really fascinating bits, the key insights, all shaped for you.
And today, we're jumping into a really crucial time.
Yeah, the early days of artificial intelligence and machine learning. We're talking, 1950s to the 80s?
Exactly. It's all about exploring that initial dream, How did we first imagine machines that could actually learn and think?
It's a big ambition. And we've got some great material to guide us. We're mainly looking at one source on early AI and ML, but also pulling in context from another, covering the broader history, cybernetics, ML, deep learning.
Right. And sometimes we can even point towards the original papers, the actual sources behind these ideas. The goal is really to give you a richer feel for this foundational era.
Okay, so let's set the scene. After that initial cybernetics work, AI and ML really kick off. The goal is huge. Machines that don't just compute, but actually learn, solve problems, basically become intelligent.
A time full of these really exciting first tries at mimicking learning.
But also some pretty major roadblocks, right? Which eventually led to that first big dip, the AI winter.
Definitely. And, to really get where we are now, you have to understand where it all started, the very first ideas.
Right. And the source material really grounds it in that initial quest, trying to understand the human brain, how we learn, and then, trying to build something like it.
Mechanically replicate it, yeah.
And one of the absolute first steps, way back in 1943, was the McCulloch-Pitts neuron, the first sort of formal model of an artificial neuron. What was the core idea there?
Well, it sounds simple now, but it was revolutionary. Think of it like a tiny switch. It gets binary input zeros and ones.
Okay.
Adds them up. If they hit a certain threshold, bang, it fires. Sends out a 1. If not, it stays quiet, sends a 0.
So just on or off.
Exactly. But the idea that something complex like thought could maybe be broken down into these simple logical operations, A and D, or R, now that was the breakthrough. A mathematical way to even start thinking about artificial brain.
But limited, right. Our source mentioned it couldn't handle certain problems.
Right. Yeah, absolutely. Things that weren't linearly separable. We'll probably get into that. But as a starting point.
Crucial.
Okay, foundational block. Then, 1949, Hebb's rule, which I always felt kind of makes sense. Neurons that fire together, wire together. How did that play into early AI?
So Hebb was looking at the brain, proposing this mechanism for learning and memory. Basically, if one neuron helps another one fire, the connection between them gets stronger.
Right.
The more they fire together, the stronger that link becomes.
Yeah.
And that idea directly inspired the concept of weighted connections in artificial networks.
So connections could be stronger or weaker, not just on-off, allows for more subtlety.
Precisely. More complex learning potential.
Yeah.
Which brings us to pattern recognition.
Yeah, our source talks about that, finding regularities, patterns in data to classify things or make predictions. Where did that fit in?
Well, it's about how machines could start to make sense of messy real-world data. Early research looked at things like the nearest neighbor algorithm, decision trees, and, importantly, neural networks.
And a key thing to grasp here is the difference from just simple pattern matching. Recognition is about finding underlying statistical structures, not just looking for exact copies, more flexible.
Got it. Okay, that sets the stage nicely. Now, the documents dive into the perceptron era, 57 to 69. Sounds like things really heated up then.
Oh, definitely. Huge excitement. Frank Rosenblatt, building directly on McCulloch, Pitts, and Hebb, comes up with the perceptron around 1957, 58.
And this was the big leap.
It really was, because the perceptron was the first model that could actually learn. It could automatically tweak its own connection weights based on data to get better at recognizing patterns.
Wow. So it wasn't just pre-programmed for every pattern. It could adapt.
Yeah.
That sounds huge. How did it work in practice?
It used what's called the perceptron learning rule. The model sees an input, makes a guess.
Okay.
If the guess is wrong, it adjusts the connection weights in a way that makes that same mistake less likely next time. It learns from its errors iteratively.
And then came the Mark A perceptron in 1960. Actual hardware for image recognition.
Yeah, specialized hardware. And they were calling it the first computer that could learn by trial and error, which, really grabbed people's attention back then.
I bet. Like it could learn to tell images apart just by trying.
Apparently so. The story goes it could learn to distinguish between cards shown on the left versus the right after about 50 tries, a concrete example of a machine learning something new.
That must have felt like the future arriving. Our source mentions a New York Times headline, "New Navy device learns by doing." And Rosenblatt predicting machines that could perceive the world on their own.
Absolutely. The hype was immense. People really thought truly intelligent machines were just around the corner. Sounds familiar, maybe.
Huh. Yeah, a little. But the optimism didn't last forever, did it? The documents point out some fundamental limits, like these single-layer networks couldn't solve problems that weren't linearly separable. The classic example is XOR. Can you break that down?
Sure. Think about XOR exclusive OR. Input A, input B. The output should be 1 only if A is 1 or B is 1, but not both.
Okay, one or the other, not both, not neither.
Right. Now, if you plot those possibilities on a simple graph, you just can't draw a single straight line to perfectly separate the 1 outputs from the 0 outputs.
Ah, I see.
Single-layer perceptrons mathematically can only learn boundaries that are straight lines. So they were fundamentally stuck on problems like XOR, which seem simple but need a non-linear boundary.
Okay, that makes sense. A major roadblock then.
Yeah.
And then, 1969, Minsky and Papert published their book Perceptrons. And our source says it mathematically proved these limitations. That sounds like throwing cold water on the whole thing.
It was a bombshell, really. A rigorous mathematical takedown showing exactly what these single-layer networks could and crucially could not do. It cast serious doubt on the whole approach, at least in its current form.
And the impact was pretty severe. Funding dried up, started the first AI winter.
Yeah, the enthusiasm just plummeted. Funding for perceptrons and neural networks generally dropped off significantly. Research focus shifted elsewhere, more towards symbolic, logic-based AI. And yeah, this is seen as a major trigger for that first AI winter.
Wow, quite the boom and bust. But interestingly, while the perceptron was hitting this wall, Arthur Samuel was working on something different with his checkers program, right?
Exactly. It's a fascinating parallel track. Samuel, an IBM engineer, started way back, maybe 49, maybe 52, working on a program to play checkers on those early IBM machines.
Checkers seems simpler than chess, maybe. Why checkers?
Good question. Samuel chose it carefully. It was complex enough that you couldn't just hard code perfect play, but it had clear rules, perfect for developing and testing learning strategies. And his program was designed to get better with experience.
It learned as it played. How? You mentioned an evaluation function.
Yes, that was key. It had a function to look at the board and give it a score. How good is this position for me?
Right.
Then it would try to make moves leading to higher scores. But the clever part was how it improved that function over time by playing games against itself, or humans.
And it used some specific techniques. Rote learning, generalization.
Rote learning was basically memorizing board positions it had seen before and their scores. Simple memory. Going by generalization was more advanced. It wouldn't just memorize, it would analyze games its own, or expert games, to figure out what features of a board position tended to lead to winning, like number of kings, center control.
Identifying important factors.
Exactly. And then adjusting how much weight it gave those factors in its evaluation function. It's actually quite similar to modern ideas like temporal difference learning and reinforcement learning.
That's a really cool connection. And it also used efficient search. Checkers still has loads of moves.
Right. Samuel used alpha-beta pruning with the Minimax algorithm. Basically, a smart way to cut down the search space, ignoring branches of future moves that obviously weren't going to be good. Not just brute force.
So smart strategies all around. And it worked pretty well. Beat a state champion. Made IBM stock jump.
It really did.
Yeah.
A huge success for the time, showing the power of this learning approach. And crucially, Samuel himself, back in 1959, describing this work, is credited with the first known use of the term.
Machine learning.
Exactly. That's where the name comes from.
Incredible. Okay, so we have these two strands, early neural nets, Samuel's learning program, but let's step back slightly in time. 1956. The Dartmouth workshop. Both our sources point to this as the official birth of artificial intelligence as a field. What went down there?
Yeah, that summer workshop at Dartmouth College is almost universally seen as the starting gun for AI as an academic field.
And who was involved? Some big names, right?
Oh, yeah. The organizers were John McCarthy, Marvin Minsky, Nathaniel Rochester, Claude Shannon, giants. And they brought together others like Alan Newell, Herbert Simon, Arthur Samuel was there too.
Wow. Quite the gathering.
Though notably, Turing had passed away and von Neumann was too ill to attend.
And the goal? Just exploring the possibility of thinking machines.
Pretty much. Their proposal talked about exploring the idea that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. Big stuff. Could machines do things like use language, form concepts, solve problems, even improve themselves?
And this is where the name artificial intelligence came from. John McCarthy's idea.
That's right. He proposed it, formalized it there. Part of the reason was to distinguish it from cybernetics, which he felt was maybe too focused on analog systems, and just to carve out a clear identity for this new research area focused on, well, intelligence in machines.
Defining the territory. So what came out of it? What were the approaches discussed?
It sounds like it was less about structured research plans and more a massive free-flowing brainstorm. They talked about everything: language, neural nets, computation theory, abstraction, creativity, problem solving, a real mix.
Sounds energizing. And two main approaches started to emerge: symbolic and connectionist.
Yeah, those became the big competing paradigms for a while. Symbolic AI, championed by Newell and Simon, was all about manipulating symbols according to logical rules. Represent knowledge, apply logic. Their logic theorist program was an early example.
Okay, logic and symbols. And
Yep.
connectionist.
That was more inspired by the brain's structure. Learning from data through networks of simple units. Think perceptrons, the precursors to modern deep learning. It's interesting, McCarthy himself actually leaned more towards the symbolic, logic-based side.
So different philosophies right from the start. But even without a single unified theory coming out of it, Dartmouth was hugely significant.
Absolutely. It put AI on the map as its own field. It brought together the people who would lead that field for decades. And it really sparked the creation of AI labs at major universities. That shared vision that computers could do intelligent things. That was the real takeaway.
But that initial excitement, that vision, it ran into trouble again, didn't it? Which brings us back to that first AI winter, mid-70s to early 80s. What caused the chill this time?
Well, a lot of that post-Dartmouth optimism, the predictions of rapid progress, chess grandmasters, perfect translation, just didn't happen as quickly as people hoped or promised.
So over-promising and under-delivering.
That was definitely part of it. Big machine translation projects, for instance, really didn't live up to the hype. And there were fundamental technical hurdles. Computers just weren't powerful enough for many tasks. And you had the combinatorial explosion problem, where problems just got too big too fast.
And we mentioned the critiques already, Minsky and Papert's book, The Lighthill Report in the UK, Cutting Funding.
Exactly. Those critical evaluations had a real impact. Perceptrons highlighted the limits of that approach, and the Lighthill Report was scathing, leading directly to funding cuts in Britain.
And funding priorities shifted in the U.S. too. DARPA wanting more immediate results.
The Mansfield Amendment pushed DARPA towards research with clearer military applications, less funding for the really blue sky, basic AI research. All these things together created a much tougher climate.
Okay, so a perfect storm, really. Unmet hype, technical limits, critical reports, shifting funding. What was the overall effect of this winter?
It was pretty dramatic. A sharp drop in AI funding overall. Connectionist approaches, neural networks were basically put on ice by most researchers. Wow.
The focus shifted heavily towards symbolic AI, especially expert systems programs designed to capture the knowledge of human experts in narrow domains. That seems more practical, more achievable in the short term. And this freeze lasted quite a while, mid-70s into the early 80s.
But you mentioned something interesting earlier, that during this AI winter, machine learning started to become its own thing.
Yes, that's a really crucial point from the documents. While AI overall, particularly symbolic AI, was maybe seen as hitting a wall, machine learning, with its focus on algorithms learning from data, started to carve out its own identity.
Sort of separating from the main AI pack.
Kinda, yeah. It started to pursue its own path. And the launch of the International Machine Learning Conference, ICML, in 1980 is seen as a key milestone. It signaled ML emerging as a distinct field.
So even in the winter, new shoots were appearing.
Definitely. And that whole period, that first winter, it's a really stark lesson, isn't it?
Yeah.
About how research can be buffeted by hype cycles, by criticism, by changes in funding. It's a fascinating arc. From brain inspiration to the perceptrons' rise and fall, Samuel's success, the big Dartmouth kickoff, and then this sobering winter. Quite the roller coaster in just a few decades.
It really is. And so much of what happened then, the ideas, the debates, the challenges, they laid the foundation for everything we're seeing in AI and ML today.
So thinking about all this history we've just unpacked, maybe a final thought for you, the listener. Consider how those cycles of huge excitement followed by, well, disappointment or reality checks in early AI. How do they echo in the conversations we're having right now about AI's future? What can we learn from the ups and downs of those early pioneers as we navigate where intelligent machines are going next?
It's definitely worth reflecting on, and we really encourage you to dig into the source materials if you want to explore this rich history even more.
Absolutely. Thanks for joining us for this deep dive.